Okay, so today we are going to look at problem number C from your daily practice, and it reads, at a sports car rally, a car starting from rest accelerates uniformly at a rate of 9 meters per second squared over a straight line displacement of 100 meters. The time to beat in this event is 4.5 seconds. Does the driver do it? All right, so we're going to follow that process like we do in class. First, identifying our object. So if we think about this car as our object of interest, we're going to identify it as the race car. Now we want to identify the time of the motion. What do we care about? When does that stopwatch start? When does that stopwatch end? So what defines our initial motion? Well, that's when the car starts moving. You might also think about this as when it starts accelerating. In this case, they're the same. All right, so starts moving or starts accelerating. And when does the motion end? Well, it says it goes a straight line displacement of 100 meters. So at the 100-meter mark is when we're going to stop caring. We need to think about what the problem is interested in. We want to know if we're going to beat this time of 4.5 seconds, and that's starting when we start and ending at that 100 meters. So that gives us our time of motion that we care about. So we next have to define the world. So we're going to define the origin. Here's our race car. It's a little slicker car than my usual cars. So there's our race car, and I'm going to set the origin at where the race car starts. And down here is our checkered flag, and so that is going to be at position 100 meters. This then defines that my car is moving in this direction from 0 to 100 meters in that positive direction. Okay, once the world is defined, we list our knowns. We make that standard list of all of our players: initial position, final position, initial velocity, final velocity, acceleration, and time. And we think about the problem and what's in that list. So, the initial position, the position when the car starts accelerating. I've defined the location of the car at 0 meters. Final position, when do I stop caring? When it hits that 100-meter mark. So our final position during that motion is 100 meters. What is the velocity at the beginning when he starts accelerating? Well, he's not moving in this race, so the velocity is 0 meters per second at the beginning. And how fast is he going when he hits that 100-meter mark? We don't know. So that's a question mark. That's not given in our problem. The problem tells us that he accelerates at 9 meters per second squared. Now that's our magnitude, and we want to do that evaluation of direction. If the object is starting at rest, moving to the right, getting faster and faster and faster, then the direction of motion and the direction of the acceleration must be the same. When an object is getting faster, the direction of motion and the direction of acceleration are the same. And what is the time? Well, it's not given in the problem. We don't know. Now we're interested in asking the question, does the driver beat 4.5 seconds in this scenario? So what answers the question, that question for us, is the variable time. Now both equations that we've learned involve time. So how do we pick them? Which one to use? So let me just write those two equations down. Our position equation. So initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. And the other equation that is powerful for us is our final velocity, which equals our initial velocity plus our acceleration times time. Now both include time, and time's what we're interested in. So which one do we pick? Well, we're going to pick the one that has more variables in it. What's going to get us to that answer more efficiently? The top one, well, I have x final, check, x initial, yep, v initial, yep, times what I want, and the acceleration. So I have everything I need but time in this first equation. That's probably a good choice. Let's just double check that second one. V final, well, that was a question mark, so I don't know V final. I do know V initial, I know acceleration, and I don't know time. So 2 unknowns in that equation. It's not going to be as effective. So let's use the equation that's most effective. X final is equal to x initial plus our initial velocity times time plus 1/2 the acceleration times the time squared. Now we look at what we know, we put it in that equation, and we can then evaluate it. So x final is 100, x initial is 0, the initial velocity is 0, times time is a question mark, so I keep that as its variable, plus 1/2 9 times time squared. So that goes away, and 0 times anything just becomes 0, and I'm left with 100 equals 1/2 times 9 times time squared. So just to practice that algebra for us, we have 100. 1/2 of 9 is 4.5 times time squared. I can divide both sides by 4.5. 100 divided by 4.5 is 22.2 equals our time squared. And then to get rid of the square, I simply take the square root. So our time is left at 4.7 seconds. We wanted to know if he beat that 4.5 record. He doesn't. So he's going to end up with second place. All right. Looking at that process again, identifying what we need to know, identifying what we care about, defining the world, recognizing those knowns in that problem that's given to us, and isolating, identifying what we are interested in, what solves the problem. Picking our equation that makes the most sense for what we have and what we want, solving that, and then evaluating. Good job.